Yeah, Kirtana, you can start now.
Okay, sir. Just when the caterpillar thought the world is ending, it turned into a butterfly. A very good evening to one and all gathered here. Here, I'm A. Keetana from the Department of Electronics and Communication Engineering, here to volunteer and compare today's webinar on the topic Insights to Mutual Coupling Effects of Panch Antenna Array using a Full Wave Electromagnetic Simulation Tool by Dr. Carlet Blair. I'd like to mention our beloved chairman, Dr. B. Babu Manokaran sir, and our managing director, Mrs. B. Jessipriya ma'am, and our director, sir, Mr. B. Sasishekhar sir, and our principal, Dr. P. Ravichandran sir, for giving this wonderful opportunity to conduct this webinar. And a special mention to our department heads, Dr. C. Nyana Kausalya ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini ma'am, Professor and Head, Lab Affairs, for their guidance and constant support. Now, let me take the honor of introducing the speaker of the day. Dr. Charlotte Blair is a technical support manager for ANSYS. She received her Bachelor's of Science in Electrical Engineering at Rutgers College of Engineering and her Master's and PhD in Electrical Engineering from New Jersey Institute of Technology. She has also supported electromagnetic simulation using industry-known tools for over 10 years. Her real-world experience extends from the design of laser diode transmit modules for Lytel to design of filters for wireless communication applications at CellWave. She is a professional, self-motivated team player committed to excellence with hearts on RF, microwave, and laser optic experience, strong field service, customer service, project management, and communication skills. With Mariam Rahmani, Charlotte serves as the technical co-chair for IEEE R1, R2 Women in Engineering Forum East. Charlotte also serves as the IEEE Connected Chair section chair for Local Microwave Theory and Technique Society and WIE chapter, as well as the IEEE Region 1 Women in Engineering chair and IEEE HKN representative. Before we start the session, a few instructions to be followed by the participants is participants kindly post your queries and doubts in the chat box. We'll be discussing it at the end of the session with the speaker. I now invite the speaker of the day to begin the session. Ma'am.
Thank you, Katana, and thank you, St. Joseph's. Thank you for having me and inviting me to give this presentations on the insights to mutual coupling effects of patch antenna arrays using a full wave electromagnetic simulation tool. Just double checking, you can hear me okay and see my slide?
Yes, ma'am.
Thank you. And to everyone, good afternoon, good evening, and good morning to those of us here on the in the USA. Welcome to this presentation that I'm having, and this meeting is being held with the support of the IEEE Antenna and Propagation Society. And so I'd like to take a few minutes to just go over the Antenna and Propagation Society. It is one of the technical societies of IEEE, the Institute of Electrical and Electronic Engineers. The tagline for IEEE is Advancing Technology for Humanity. Now, it is the largest technical industry society, and currently there's over 400,000 members. There's 419. This was the last statistics that I saw, which was just this week, midweek. And it has a global reach. IEEE is active in over 160 countries. There's 46 technical societies and councils, APS being one of them. And as I heard, the St. Joseph's as the IEEE branch is involved in many of these societies, not just the APS society. And for student members, there's over 124,000 student members. And you could see that out of the membership, there's a good about 25% are student members. Also, the IEEE not only has a global reach, it also has a technical breadth. It was, 1,900 face-to-face annual conferences throughout all the many technical societies, over 5 million technical documents, and over 200 periodicals, including many of the transactions for each of the societies. Technical documents, I forgot make sure, as a university, a lot of the publications are available on the Digital Explorer as well. And one of the known things about IEEE is that it participates in standards, and that is 1,300 active standards. And for this talk on antennas, one of the emerging trends is 5G, whether it's 8S or V2X, and they just have a new standard for 5G just recently, say within the past month. Now, for those who are not familiar with IEEE and IEEE regions, IEEE has a global reach. And so they have these regions, and regions 1 through 6 is in the US, region 7 in Canada, region 8 through Europe, and region 9 in South America, and region 10 throughout Asia and India, Asia Pacific. And the breakdown, as you can see, it's maybe hard to read the numbers here, but the intent was to show you that both region 1 to 6, which is the US, as well as Asia Pacific, top the number of members in the IEEE APS Society, both about just, 3,700 in the US and 3,100 in region 10. So these are the two pillars of IPS currently, and these are the regions and the amount of members that we are currently looking at. And these are active IEEE Antenna and Propagation Society members, so over 10,000. And with that, the APS societies, as well as all the societies within IEEE, have regional coordinators, and they are to help support these type of technical meetings. And uh, fortunately or unfortunately, with the pandemic, we have meetings that are now virtual, but it does enable us to have, again, a broader reach and a more global reach throughout the regions. And now for this year in APS for 2020, the APS Chapter Activity Committee is being led by Dr. Ajay Potter. And for regions 1 through 6, I am one of the regional coordinators. And for region 10, we have representation both from China as well as in India. So these are all our regional APS coordinators who are trying to, they can help you coordinate meetings, get you speakers, or they're there to help enable the advancements of the APS society. I do want to show you we are inclusive and we are diverse. Out of all of our coordinators, 6 of them are from industry, 8 are from academia, and we do have student representation as well with a graduate student. And the breakdown, and I was very glad to hear in our discussion before this meeting that there is a high percentage of women in the St. Joseph's. I think the APS society is maybe it's in the single digits, it's less than 10%. But as a representation on the regional committee, on their AdCom, we do have 3 women and 12 men on this chapter, on this activity. Okay, so again, thank you, IEEE APS for sponsoring and IEEE student chapters for having this meeting. Okay, now on to our talk today. And so this is a brief outline of what I would like to talk to you today about. I am going to focus on 5G, autonomous driving, and V2 vehicle to everything communications that is enabled by an antenna structure, whether it's, an array or the electronics around it. We will go over, the review of microstrip antennas. will use a electromagnetic simulation tool, and in this case, ANSYS HFSS, to characterize these microstrips, and specifically the antennas. We'll look into antenna arrays, giving you an idea of what characteristics you should be looking at. And then I'll end with a summary with any questions. Okay, so what I'd like to do first is, before I start talking, let me just show you a quick video. And let's see if that video will come on. Maybe when it's broadcasting, it's not going on. Oh, there it goes. Okay, user error here. Okay, here we go. So let me make sure it's playing. I don't know if it's buffering on your side. I don't see anything on my side here. Can you see the screen?
No, ma'am, it's not visible.
Okay, let me try it again. It's just, I could see it coming on in the background. It's probably slow to buffer. Huh. A little bit of technical difficulties. It is slow. I see it coming in the background on my side, but it is a little grayed out. This was, let me see if there's a another way of doing this. I'm going to do a quick share and unshare of my screen to see if that will help. So let me just quickly unshare this and then go ahead and share again. Okay. Okay, there. Can you see my screen now? Hello?
No, ma'am, not yet.
No, ma'am.
Oh, and see, I can see it on my side now.
Now you just
Not shared.
It's not sharing. Okay.
Yes.
present screen. Okay, ma'am. Now it is
Now,
coming.
now, okay.
Now it goes on. Oh, okay. Just a minor technical difficulties. It did show before. Let me just start it from here so it doesn't. It does not seem to want to play with the while I am broadcasting here. Now in our testing, it did play. Okay, so what I had intended to show you was a video that some of my colleagues made for the IEEE MTTS conferences, one of the conferences that we had, and it was a student contest. And what it was about was a quick 60-second video on some of the applications that the students were working on. And this happened to be about ADAS and autonomous driving. And when we talk about, autonomous driving, we're talking about not only the car guidance, right, but communications between the car and everything else. And this is enabled, and in this instance, is described here with the far field radiation pattern. With it under the bumper, there is a patch antenna element in an array that is mounted on the front bumper of the car here. And hopefully I can, did it go through? Is it playing now? I think it may have buffered.
Yes, ma'am.
Perfectly. So it had to buffer a bit while it was on there. And so you could see that for autonomous driving, you could see the car guidance. You see the car here, the streets, and you also see, the other vehicles. So the safety and the reliability of the autonomous system is dependent on that design of these antennas. And in these antennas, you could see they're very pointed and very directed. And that is a beam forming because it's not only in one direction, it has to do a full, be aware of all of its surroundings. And when I say the surroundings, I mean other vehicles, perhaps other obstructions in the way, whether it's, the side rails or another person, or it could be the entire platform or the entire environment. Guidance within this is to be a cityscape. And when you say it's a landscape, there's a lot of scatterers that can interfere with the propagation of the signal that either the antenna is transmitting or receiving. And that signal sees several different bounces, as you can see by the different colors of the rays of the signals being bounced off of all of these building structures. Okay, and these are all of different materials. And including when the car is moving here, the detection of the edges, including the reflections about the corners, have to be included. And this is not just a static scenario where you're saying, oh, the car is here and maybe, and these could be cars or smartphones. It doesn't matter. It is a dynamic situation. And it is not only between one or two transmit or receive pairs. There could be hundreds of receive pairs, whether the antennas are on ground, and as you saw on that one, it can also be up in the air on the many of the low Earth satellites that are now being developed for the 5G satellite type of design as well. So antennas have to work as intended, from point to point, whether it's from not only, it's very rarely line of sight. It is scattered. It has scattering effects. There's propagation effects. There's attenuation, distortion of the signal, and distortion not only from the reflections of the signal, but also in the fact that there may be, as you saw, many transmitter and receivers, many other wireless signals that come into play, besides the intended signal for communications or guidance that you're looking at. And so one of the last scenes that you saw in that video was this car, and you saw the 2D cut as well as the 3D cut of the antenna gain pattern. And this formed beam is what antenna designers are trying to make sure that it is very directed with high gain to meet all of those losses, all those scattering effects that they see in the environment. And the industry is depending on students like yourselves and professionals to enable them with new ways of implementing these antenna elements as well as these structures. So in that car that you saw, when I tried to point that out, I wanted to make sure you saw the far field is enabled by an array of antennas. Okay. And you can see here that if I zoomed in on that, what we actually see is an array of antenna elements. And in this case, these are planar type of structures. Okay, so what we have here, shaded in blue, is a radome, something above the antenna element and the array and the electronics to protect it from the surface. 9 times out of 10, it's not very visible, and it is probably behind the bumper of that car. There are several key locations that these antennas are located. It just so happens that I put it on the front bumper. Does not mean there are not antennas that are on the sides or on the rear bumper of the car as well. And many of these structures here are patch type antennas, and these copper looking colored squares happen to be the radiating element itself. And now if I look just at the element, just at one single element, this is the structure of the antenna element itself. And this is the critical design part of the structure. Yes, we're concerned about the array and the coupling of the elements to itself and to its neighbors and to the environment, but the design of this element is very critical. And we can see here, this here rectangular patch is indeed the radiating element. That is what is giving off that radiation pattern, that very colorful balloon-like radiation pattern that you see here. But this is in no way just the only shape that the radiating element can be. Here it's rectangular, it can be square, it can be circular, it can be a disc, it could be a semicircular disc, it could be an arc, it doesn't have to be, you know, half an angle, be just a sector. And I have also seen triangular. And now the design of these arrays and these elements, like I said, are waiting for you to come up with some unique design, okay? But they are not, by definition, it is some shape for the conducting patch that is sitting on some dielectric, and the dielectric could be any type of board material. It doesn't even have to be a board material. It could be suspended in air to have a suspended type of antenna. So it's two metals, one acting as the radiating element and one acting as a ground plane on some dielectric. And in most cases, for mechanical stability, it is some harder board material. It can be conformal, so it does not have to be flat in the, if I call this the XY extent. And we'll see later that there's been a lot of research, and if you Google antennas and antenna arrays, there has, you know, years and years. And, you know, I have, when I was in school, my go-to book was Dr. Balanis's, you know, antenna theory book, and all on antenna design. And as long as you can mathematically model these shapes, you can theoretically get an idea of what you can expect for your radiation pattern. And sometimes it may be very hard to capture that mathematically. You know, these very different designs. I've even seen S-shaped type of designs and crescent type of designs. And then you have to characterize them mathematically as they are in an array. So it sometimes is easier to draw out the shape and use an electromagnetic simulation tool to characterize and simulate the response of these type of structures. And again, I will be using the ANSYS HFSS electromagnetic simulation tool. I am an employee also, my day job, and I really work for ANSYS and not just IEEE, but they have this tool, an electromagnetic full wave simulation tool, that will assist in the characterization of the antenna element as well as the entire platform or the structure of the antenna. Okay, I am trying to go to the next slide here. Here it is. And within this tool, you know, like I said, years and years of study and research that has already went into characterizing these elements. And so we don't have to start from scratch. And there are toolkits, you know, that and software tools that enable you to characterize and draw these elements up, and whether it's, you know, commonly that they're rectangular or square, they can come in, you know, a different feed type. So this is a probe fed. This has an inset feed line here again, but still, you know, very rectangular. These dimensions have been mathematically modeled. They can be circular in the same fashion. Here we have a, you know, a feed that's a probe fed, Also, we can have an inset fed here for a circular patch antenna type of array. All of these, again, are microstrip type of antennas. They could be a microstrip fed antenna. It doesn't have to be an inset where you're also have other attributes of the geometry that comes into play here. As you go along in your studies and you're in the lab, you find out that these microstrip lines look more like inductors, and these here gaps between the feed line and the antenna metal, the radiating, it looks more like a capacitor. And so we go back down again. When I say mathematical model, I include that to include circuit theory. What do these look like as a component? Yes, I can characterize this as an inductor. I can characterize this as an inductor with a capacitor as well. And these, again, are just single elements. We're looking for higher gain. And a way to get higher gain is to increase the number of elements that you have in your antenna structure. Again, it can be of a rectangular type of structure. It could be circular. And there are many types of antennas. And today we're only focusing on the microstrip type of antenna, a planar type of antenna. Again, for the ADAS or 5G application, because it needs a very low profile. We can't have those big horn antennas. We can't have those parabolic dish antennas sitting on a vehicle. So we have to think about the structure, the physical structure of the antenna element as well. And so these planar type of geometries, these microstrip type of geometries, lends itself to this type of physical specifications. Okay, so if I go to just the most fundamental form of a patch antenna, again, using that same element that I showed before, we're looking at a radiating patch. And this is dictated, the response of the antenna is dictated by the size of the patch, by its length and by its width. Okay, and when I say by its length or by this width, we have found that that is dictated by the operating frequency that you want your antenna to work at. Okay, and so we say it is about, again, it's very heavily dependent on the geometry and what the element is coupling to. And I say it's about half a wavelength, both in length and as well in width. And there are other delta L's or, delta length and width factors that come into play. And that depends on what we call the fringing fields. Now, you may have heard of fringing fields before, but I just want to go and emphasize this. You may have seen, this top picture here, which is the electric field. So these little arrows here are to describe the electric field, how the vector form of the electric field, how the electric field is propagating between these metal surfaces. So this is a four-sided metal surfaces, and the metal contains the electric field inside itself, and it goes from top to bottom, and it's very straight. So mathematically, maybe very easy to define. And we have heard of different type of polarizations, whether it's TE, TM, or, TEM or Quasi-TM. But these modes we can mathematically describe. Now, opposite to that is the phenomenon of microstrips. Now, microstrips typically have, a metal trace, right? That metal antenna element on the top, but it doesn't cover the top surface as in a waveguide. Okay, so what we have here is this is fully covered by metal. Here we have partial coverage of that top surface with the metal. And this is the top of the dielectric here. This is some dielectric. So this allows, it's non-conductive. It allows the fields to penetrate and radiate outside of the metal. Okay, and inside that dielectric, again, inside the metal top of that element and the bottom ground, can or does it does not have to be a full metal ground. They have what they call defective grounds, or it's not a full conductor. So you can have these patterned
Ma'am,
grounds.
sorry for disturbance. Screen is
Yes.
not visible.
It stopped sharing.
Yeah.
Okay. Let me try that again and reshare. Let me know if that shows. I wonder if it's
Yes,
a
ma'am. It
slow
is
network.
showing.
Okay. Thank you for letting me know. Please tell me I don't have a second or third screen here where I could see what you're actually saying. So thank you for that. Do let me know if there's any issues.
Definitely.
Yeah. Hopefully the audio doesn't go out. All right. So in this structure here, I'm trying to emphasize the fringing electric field here. Okay. And so you could see that in this case, that we no longer have a straight line depicting the electric field straight from the top of the metal to the bottom of the metal, because we have a dielectric and we have what these called these fringing fields. And yes, the colors are different to describe the different magnitudes, but it's actually the direction of the fields that I want to show you. So there are fields outside of the regions between the two metals. And this is what we call the fringing fields. And these fringing fields are what matters. This is what is actually radiating out. This is actually what we call the microstrip antenna that's radiating out. And in some cases, we want these radiated fields because we're actually going to enhance the coupling between the elements. And in some cases, we don't want any coupling, and we call it parasitic coupling. So depending on your application, these fringing fields are either wanted and necessary there by design, or they are not wanted. One of the effects of these fringing fields is that it artificially increases the length or width of that patch antenna. So if I went up here, this is the physical length, the dimensions, a finite number for this patch, whether it's the length and the width. And I said, oh, it's about lambda over 2 with some other factor. That some other factor are these fringing fields and how they are coupled or terminated, or if they are radiating out. And so those are what may be hard to dictate in a theory or in mathematics. And so we use these electromagnetic simulation tools so that we can visualize these fields to actually see what's coupling. Before, when I was showing you the elements, I said, oh, this length of line is inductor. And over here, these inset feeds between these two metals are capacitor. I didn't learn that in school. You learn that in practice. You get to see geometry, and you can boil it down into the components. Say, oh, this is really a series inductor, and this is actually a shunt capacitance. And this is something that you get as you start actually working with these elements, actually playing in the lab. So as you're studying, I am very heavily into lab experience. Go in there, tinker around and really understand how the signals are propagating and what's happening, because those insights are really what you're going to use to help design different type of structures. It's not the ordinary square or circular structures that we want. We want all those other different type of structures and innovative ways to couple them. Okay, and so another thing that we're looking at that these fringing fields does is because it's increasing that length of that patch, and I was saying, well, that's going to dictate the resonant frequency. What I did here was I just parameterized the different length of that patch, and you could see as I lengthened it, it actually decreased the resonant frequency, and each color is a different length. So I parameterized, and you could see the response. Yes, it's doing what, theory says, lambda, is 2 pi, c lambda c over f, and that c is the speed of light in the material. And so materials matter, right? So it's over the square root of the relative permittivity and permeability of that material or that dielectric that patch is sitting on. And I bring that up because part of that extra factor that comes in designing the physical dimensions as a patch Also, what we see sometimes as whether it's delta L or delta W, we sometimes see it as the effective dielectric constant. And that effective dielectric constant is also dependent on frequency. So it's these fringing fields. It's a property of the material, board material itself. It can be frequency dependent. It can be orientation dependent, whether it's in the X and Y or whether it's in the Z. So materials come into play in their structures, and these matter. You know, it may be hard to see my frequency scale. I'm only looking at 1 gigahertz. But let's talk about it. I said 5G and I said ADAS. And so a question may come up, why the heck is she looking at 1 gigahertz? I'm trying to stress a point here. 5G currently, and again, the standards have been changing. There's 2 frequency ranges for 5G. We have what we call the 5G new radio, which is the sub 6 gigahertz range of frequencies. Will always be there. Our infrastructure for our communications is there, for our wireless communications is there. I showed in that video, I want to point out again, I had satellites in the air. Those are at the new radio or the sub 6 gigahertz type of frequency range. You saw the ADAS, the many radiation patterns that you saw, you know, that can be within the room or within the locally, you know, on the streets, communications between smartphones or devices. Those may not be at the sub 6 frequency range. They may be at the millimeter range, or that is what we're designing. And there are some that have been already for 5G have been shown to be, depending on where you are regionally, it could be 25 or 26 or 28 gigahertz. Okay, so those are for communications. The ADAS systems are actually closer to 77 or 80 gigahertz. So depending on your application, that dictates the frequency range you're in. And each range has advantages and disadvantages. And one of the biggest disadvantage of millimeter wave is the higher the frequency, the shorter the wavelength. And guess what happens? Then you have a shorter distance that it can propagate before it attenuates. So you can't go very high and with, you know, millimeter wave type of communications. Okay, that was just little diversions on frequency range and why it matters. Okay, going back to what we really want to see in here are the impact of the fringing fields. So I showed you the vector, and you saw that the vector radiated out into the dielectric, but what we really want to see is the electric field. And here in this image here, I have the magnitude instead of the vector of how the fields are propagating. I have the magnitude of the electric field here, red being the highest and blue being the lowest. And just to see how the electric fields, I'm going to try it. I'm going to play this and see if it works. Didn't seem like some of the video. I think it's a band limiting, but this is a animation of the electric field. And what I want to point out here is red, that's where the radiating field is. That's where the field sees an open end, and that's where the radiation gets launched out. And as a matter of fact, we want to see those fringing fields. Remember I said it's the fringing fields that I'd like to see when that's giving off the radiation. And if I were to look at it as a component, it's an open, so I may see it as a capacitance that it's actually launching into the air. And again, one of the one of the things is I want it to radiate out. This is a radiating element. So I want most of the radiation to go into the air above that patch. And so that comes to say that the thickness and the dielectric constant of this board wants to be of a low permittivity. And why do I say that? Because again, I don't want the fields in the dielectric that's between the patch antenna and the ground. I want the radiation to propagate out and above in some form or fashion. Okay, so I want it to be of a low permittivity. And if I were to look again at another picture of the fields here. So I just put 2 other cut planes to emphasize a point here. If I zoom in on the corners where I can see what is below the patch, and again, this is the magnitude of the electric field. This being the dielectric, I can see that there are fields in that dielectric, and this is the fields above it. Just notice that, yes, there are fields above and below. We want it above because we want an antenna. As long as the permittivity of that dielectric is low, the fields will not stay within the dielectric. The dielectric, if it's a higher than epsilon r equals 1, which is air, it traps those fields in that dielectric and it harnesses it. We don't want that in this case. We want it to actually go out and radiate. And you again could see that there are these fringing fields. They're not straight lines up and down. They're not the same color. So you see that there is fringing. And if I had another element or another trace here, you could see it starts to couple with each other. And that, again, that is what we want or we don't want, depending on how we're going to go, depending on our applications. Okay, and so what, what I've been showing, what I was saying up here in that toolkit on easily making some geometry is what we call this probe-fed rectangular patch antenna. And so if I go behind it and I take away that patch, I see this, how that the signal that is going through this coax pin is connected to that patch. It actually sits on top of this pin here. Okay, so the patch is connected directly to the signal pin on the other side. So there's another a connector on this type of feed network. Okay, and in our case here, we had copper on top and bottom, and we had some sort of dielectric in there, and we're feeding it with, again, some other dielectric, which may be Teflon and a coax connector. Again, we have different dielectrics and the fields are propagating, but this time in a coax, it's contained within that connector there. So we have the signal in the Teflon that goes through the dielectric board that tops and connects itself into that radiating element. So there's several different transitions that the signal sees. And in our courses in electromagnetic theory, we always talk about interfaces and surfaces, whether that boundary is dielectric conductor, or, multi-level. And every time you hit a boundary condition, you're going to have a change of impedance. And if there is a change in impedance, what's going to happen? You're going to attenuate that signal. You're going to distort that signal. So every single time that we have a boundary condition change, a change of mixed dielectrics, we're going to modify and disturb that propagation of that signal, something that is mostly unwanted. And so this is a type of connection that we call contact, because that signal pin is actually touching the radiating element. And that was a coax fed. There is also what we call a microstrip fed. Here's that inset fed antenna that we're talking. So if the connectors, that coax connector cannot be placed on the flip side of that bumper because there's no electronics on it, it's actually attached to another board, we may actually have to go through a feed line. And just the way that application is, instead of coming under the board and having the connector there, we actually have to come into the feed line. So it's the actual physical platform that we have to consider that dictates the way we're feeding this line. But here again, the signal is physically attached to the radiating element. There are also what we call non-contact feeds. Right? And in that, we could have what we call a slot-fed antenna. And so again, this one is of a microstrip line that carries the signal. Above the signal, this is a microstrip trace, which carries the signal, and we're looking for transmission here, and we really don't want it to radiate out. But in this case, it is actually radiating out into this slot, and that is how we're coupling the signal into the radiating element by a microstrip trace line underneath it. And it's not physically touching. This trace is not physically touching that slot. It's the fields that are radiating out that's coupling the electric fields onto that radiating element. There are other structures, and perhaps some of the professors there, I took this from a published paper from IEEE. I looked up Chennai, and it was very nice to see that at St. Joseph's that you had a paper in the IEEE publication on this multi-layer stacked antenna. So again here, non-contact, you had a radiating patch. It, again, some sort of cutout for different type of enhancements that you were looking for, different ways. It was a coax fed, but you could see that for different reasons, we have some capacitive stubs here, either to tune the bandwidth, change the resonant frequency. But here, each of these square patches above the radiating patch are not in direct contact with the direct feed. And so this is another non-contact type of configuration for an antenna structure. So again, as many ways as there are of feeding the structure, there are many shapes. Again, depending on your application will dictate how we're going to feed the radiating element. But it is safe to say, typically, no matter how we're going to feed the network, if it is a patch antenna, you're going to be able to see that it is, again, and we're going to try to play it, it's going to have this same type of characteristics where we're going to have the fringing fields about the sides of the patch. Here's the signal coming in, so it sees this as a more capacitive here, again, a parallel plate, so to speak. And then you could see that it's going to radiate out. Again, a picture of the electric field that is radiating on the top patch of that antenna. Okay, so now if I go back and I look at this element and I look at the design of this element, I also want to think, okay, what's going to characterize this? I kept saying, oh, radiation pattern, and there are different radiation patterns that I want to see. We may want to design a isotropic type of antenna, which it radiates out in all directions, and we may call it the red apple type of radiation pattern. But in some cases, we want it to be more directive, right? We want to direct that beam in one direction. And we may have a series of these elements or a series of arrays acting together to cover, 360 degrees, but very directed. And just like with a balloon, you squeeze it and, you get higher gain as it becomes more directed. One of the characteristics of these antennas that we were talking about before is that resonant frequency dictated by the length in the patch antenna case, right? We want to see what the radiation pattern is, how much area we're going to cover, okay? What is the gain of that antenna? And I want to look at the impedance. I want to look at the impedance of that antenna structure, the feed network, what it sits on, and I can use the Smith chart. I like using the Smith chart. I like looking at the frequencies, and the Smith chart enables you to not only to retune your structure to see if you need more capacitance or perhaps you need more inductance to tune it to a specific frequency, but there's a lot of other circuits or circuit elements that you may want to attach, and you have to make sure that impedance is matched so that you are not losing any signal. The other one that I didn't mention or show here was polarization. Again, are we radiating in the, transverse electric in the TE mode or the TM mode? But I will tell you, for most antennas, especially the wireless antennas, every time we reflect or it's scattered, it's changing phase. So whether it's started out as TE or TM or vertical or horizontal polarization, we actually want what we call circular polarization. We want to include both, because as it's scattered, not only are we losing attenuation, we are distorting and changing the phase. And so we may not have the exact polarization. So we want to include all polarizations in that antenna. So the design of the radiating element is very, very important. You know, this presentation is on antenna arrays, but that is so heavily dependent on that element design, that feed network, and the element-to-element coupling of that array. The array sits in some sort of pattern or in some sort of fashion. And again, antennas has been, studied for decades. And there is what we call an array factor. And so with an array factor, we assume for mathematical simplicity that the radiating elements are all identical and they are in a linear type of fashion. And so we're saying, okay, same element, linear, and we could get an idea of what the radiation pattern may look like for an array. In the very simplest term, it's, the array factor just combines all of the radiations of each of these elements, of course, with some weight factor in there. But that is really too simplistic. And again, that's this coupling between the array is what you need to be aware of and what you really need to design. And a lot of this is dependent on the geometry or the platform that it sits on. If I were simply to take that element and put another element either, quarter wavelength or to a wavelength away from each other, I could easily see not only do I detune it, I change the resonant frequency, I also have some attenuation. I may or may enhance depending on the distance between the elements. And yes, there are some rule of thumbs. Again, this for a linear array with a set spacing between all of the elements may be easy enough to model, but sometimes we don't have the luxury of a linear array. We may have to put it, we only have a small square footage that we have to have the array in, and so maybe we may have some sort of rectangular array, n by n array, or we may have to put it in some sort of nonlinear fashion. Okay, and so we need to dictate the overall coupling of the element to element so that we can create the resulting gain to what we need for that application. And I have down here, it does depend on where that element sits. Is that element, and I'm going to go to this next slide, is that element on the edge? Does it see its nearest neighbor, or is it on the corner and its nearest neighbor perhaps is just air? Or could it be surrounded? Like if I doubled this, could it be one of the interior? Each of these have different coupling effects. So the coupling effects between element and its position and the finiteness of this board, because again, we have fringing, right? There's fringing not only between the field between the ground plane and the metal, there's fringing between the elements. And at the edge here, we have the fringing to the edge of the board as well as this other dielectric, which is air. So we have fields that are radiating out of the board that radiates out into the air. So the finiteness of the board also has effects as well. And things that were, after a lot of tuning for this one, I have only a 2x3 array, only because, I had to go in and I, just like with the length of that antenna, I had to parameterize it and optimize it so that the spacing will give me a nice radiation pattern and that they all resonated at a certain specific frequency. Again, remember that as I couple them, I have a distortion between each of these elements because they are affecting each other. If I pull them away enough, then they each resonate at the resonance that it was physically laid out for. So coupling effects do come into play when we put these elements in an array here. Again, something that an electromagnetic simulation will help enhance. It gives you a visualization of how they're coupling, not, just the fields itself, how are they coupling? What other components is it coupling to? Maybe it was an unintended trace. Maybe it was the housing was coupling to the sidewall of the housing of another element, whether it be electronics, whether it's an amplifier, or it's just the part of the body of the car. So some insights that I wanted you to take away with. We need unique designs in the radiation of that element itself. And it is indeed very important to consider that spacing between each of that elements. What is that distance that we're looking at? We have to look at the position of that element in the array. And all of our mathematical equations are a great start value, but it doesn't include all of the coupling, and they're nonlinear. All these fringing and parasitic effects that I was trying to show you and emphasize that happen just because of the way the radiating element is implemented. Okay, so there's always plus and minuses of the different geometries that we're looking at. And this is why, you're learning the basics in schools, just so that we can, again, I'm going to emphasize, we need different designs so that we can go forward to 5G and beyond, because we need different elements. We need different designs so that when we have these losses, whether it's from scattering or any of these propagation losses or just system losses or interference from other signals, that we can indeed have the correct gain and it's directed. So again, very important to enable us, especially in this climate, right? We're having this meeting, a virtual meeting, as a response to the pandemic. What's keeping us connected? Why? It's wireless communications. I'm sitting in an office or at home, and I am connected wirelessly to all my devices. They're wireless signals, and I'm heavily dependent on it. And that's because I've incorporated not only the functionality and the specification of the elements, I considered the environment that I'm in, indoors as well as outdoors, right? Infrastructure, when I was saying, 2 frequency bands for infrastructure, infrastructure is at 1 frequency, because they all can communicate together. So a very, very enabler of current technologies is antenna design. And so electromagnetics has a lot to play into there. And again, electromagnetics is not I see that it's very popular there at St. Joseph, but we don't always have a lot of students in electromagnetics. It's actually discouraging, because wireless and its applications are booming. We need more students of electromagnetic theory. And so one of the things I just want to get a little plug for ANSYS, again, my employer, who is trying to also be enabler of education for electromagnetics. We have on our website on office ansys.com/courses, we have these free classes to add to what your instructors are teaching you. We have a few of them online. We don't have all our courses online yet. And they go over simple as electrostatics, magnetostatics, transmission lines, to help give you an insight onto what electromagnetics is, some of the base theory classes, and we will also have some application classes. And for students, always encouraging students to get into electromagnetics. ANSYS being a simulation house, we offer free student software. So if anything, go ahead and download the free tools. The free software doesn't include all the features of HFSS that I was showing you into here, but it includes all the physics. As soon as we talk about any type of structure, when we're in industry, we're going to think more than the expert design engineer, whether it's for antennas or electronics. We have to talk to the other engineers, the other physics. We have to know that it's radiating. There's electronics behind it. It's going to heat up, and the characteristics, that length is either going to increase or it's going to bend and it's going to stress. We have to talk to the other physics. We have to know what's going to happen to that those devices when it is in a thermal, heats up, or if there's too much power, causes that element to heat up, or it's in an environment. It's in the middle of the desert, or it's over there in the snow. So the outside climate comes into play. Besides, what we were talking about, signal propagation. So temperature comes into play, and airflow. We have antennas, right? Right down here, the antenna masts here are up on it, and have wind effects. they are going to sway and flow a bit, and it's going to, either in this case, if it's windy, it's going to reduce it, or if it's just in the desert, it's going to heat up. So these come into play. We have mechanical fluid as well as electrical components to every single structure that we need to consider for this technology. And again, I just want to end it here. I want to thank you. I want to thank you for listening to me today as I discussed, a little bit about antenna elements and about antenna arrays. And I want a big thank you to St. Joseph's, to all the students, to all the professors who help coordinate this, to IEEE, APS. I want to also thank, ANSYS for allowing me to do this. And, Katana, I don't see the question and answer on my dashboard here. So please, if there are any questions, go ahead and ask.
Yes, ma'am. Thank you for sharing your knowledge, ma'am. And let's move on to the question and answer session. The first question is, what is the major lobes in vehicles attached with an antenna?
The major lobes? Well, depending on the functionality again. If it's a very directive antenna, we don't want those lobes. We don't want side lobes. We don't want back lobes. Why? Because those may be fringing fields that may cause parasitics and couple to other components in your systems. So what modes? Let's consider the main lobe, because more applications than not for this application's 5G and ADAS, we want a directed beam. So I'm going to look at the main lobes and I'm going to tell you, no, we don't want it to be isotropic. But if that antenna is more of a sensor and it's for guidance, and perhaps it's on the bottom of the automobile on the car, and it's actually a sensors on the road, well, I don't want it to be directive, and I may want it to be more isotropic, and I want it to be more of that balloon type, because the application is a sensor and it's not directed. So I'll have to say, which mode depends on your application.
Thank you, ma'am.
A long-winded answer. Go ahead.
Yes, ma'am. The next question is, how do you monitor vehicle intensity on the road?
Oh, it depends on the vendor, right? So are different techniques. Are you looking just at magnitudes of the fields, or are you looking at phase differential? Different techniques.
Thank you. The next question is, how do you design antenna arrays for vehicles, vehicle distance maintenance on the road?
How do I maintain the array or design the antenna array for vehicles?
Vehicle distance maintenance, ma'am, for designing antenna arrays.
Well,
how do you maintain distance between one vehicle to another vehicle by using antenna design, ma'am?
Okay, again, here it's going, when we talk antenna distance, and again, depending on frequency, it's a very, again, application specific. Vehicle to vehicle, are the antennas in the far field? But if it's a vehicle to vehicle, it may also be in the near field or the very near field. And those array have different characteristics and different considerations, more detailed considerations than those antennas that we're designing for far field. So in short, the difference between the near field and the far field, it is lambda, dependent, again, frequency dependent. So it's not just distance. It's, again, depending on the application and the frequency. It's the field view of the antennas, near field being more complicated than the far field, because in the near field, we cannot make the assumption that E and H are orthogonal to each other. So again, how do we keep the distance depending on the technology, and if it's near field or far field, and what distance is there to be used at? I hate to say application specific, but they really are.
Okay, thank you, ma'am.
Thank you, ma'am, for clearing our doubts. And it's now time to express our gratitude. I am Kirtana A from the Department of Electronics and Communication Engineering, St. Joseph's Institute of Technology, St. Joseph's Group of Institution, and the entire fraternity of the institution. I extend a hearty thanks to Dr. Charlotte Blair for sharing her knowledge on this webinar. I once again thank you, ma'am, for sparing your time from your busiest schedule to grace this occasion. My
Big
heartfelt
thank.
thanks. Yes, ma'am.
Go ahead. Sorry.
My heartfelt thanks to our beloved chairman, Sir Dr. B. Babu Manoharan, sir, for his consistent upkeep in conducting this webinar. My sincere thanks to our Managing Director, ma'am, Mrs. B. Jessipriya, and our Director, Sir, Mr. B. Sasishekar, and our Principal, Sir, Dr. P. Ravichandran, for giving this great opportunity to conduct this webinar. And a special thanks to our department heads, Dr. C. Nyana Kausalya, ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini, ma'am, Professor and Head, Lab Affairs, for their support. Last but never the least, I thank all the participants for their active participation. This webinar will be continued tomorrow by another eminent speaker, Dr. Chinmoy Saha, on the topic Near and Far Field Wireless Power Transfer, Trends, Techniques, and Recent Developments. Interested participants can register through the same link. Once again, thank you one and all.
Thank you to everybody again. Thank you for having